a route through Eatonville, and Packwood is also shown. I have never been to Eatonville and Packwood, just saying.
Packwood?
Packwood, that's what it says. I don't know, never been there. I have been to North Bend. I've never been, I probably drove through Mount Rainier. I don't know. Okay. But I've been to North Bend. All right, so what they do is they start at Y. So they mark Y with a distance of 0. So we're working backwards. We want to get from Tacoma to Yakima, but we're going to start at Yakima and determine what's our best optimal route to get between the two. Okay, mark it with a distance of 0. The distances will be recorded in brackets after the vertex name. Okay. So our first step tells us mark that, designate that as our starting point. So step 2, for each vertex leading to Y, calculate the distance to the end. For example, North Bend is 104 because it's 104 miles from North Bend to Yakima. Okay. If I'm saying Yakima wrong, it's the way I grew up saying it, so just be happy. And MR is 96, and Packwood is 76. Remember, the distances in this case refer to the travel time in minutes, not miles. Okay? Did I say miles? I think I did.
Yeah.
All right. So we mark Y as visited, and we mark the vertex with the smallest recorded distance as current. Well, that's P, right? Because P has the smallest distance of those three. Okay? And we go back to step 2 then. Okay? So you notice here it says step 2, number 2, because we've looped back through this algorithm. Right? So here we are, we're at P. For each vertex leading to P and not leading to a visited vertex, this is visited, we're done. We're out of Yakima now. We find the distance from the end. Since E is 96 minutes from P, and we've already calculated P is 76 minutes, E is 96 plus 76, or 172, okay, minutes from Y. If we make the same computation for Mount Rainier, MR, it's going to be 103. Since 103 is larger than the 96 that's already there, we don't replace it, okay? We keep it there. We mark P as visited, and we designate the vertex with the smallest recorded distance as current. So now P is visited, it's crossed off. Now we're looking at Eatonville, Mount Rainier, North Bend. Mount Rainier's the smallest, Millie.
Where'd you get 103?
103 was we took 76 miles to Packwood, and then we added 27. That's where that 103 went. But we don't replace the 103 because 96 is less than 103. So we're keeping the 96, and we're not talking about the 103, okay? Because we want this least amount of time, okay? And so since 96 minutes is less than 103 minutes, we just don't replace the 96 with the 103. I know it gets confusing, people. It does. So now Mount Rainier is for each vertex leading to, so that's our current one, is Mount Rainier. Packwood's visited, Yakima's visited, we're at Mount Rainier right now, okay? For each vertex leading to MR, and so this is step 2, number 3. This was step 2, number 2, then we did step 3 and 4. Number 2, now we're at step number 2, number 3. We're looping back again with this one current. For each vertex leading to Mount Rainier and not leading to a visited vertex, so we can't go back to Packwood. We go to any other vertex we haven't visited. We find the distance to the end. 96 plus 79 gives us 175. And that's all we can consider, because that's all that attaches to Mount Rainier. Since we've already visited Y and P, that's all we can do, okay? And it's 175 minutes. So now, we mark Mount Rainier as visited, and we designate the vertex with the smallest recorded distance as current. So what is our smallest distance now? If these 3 have been visited, we're not looking at any of these 3. We're looking at 172, 140, and 104. 104 is our next one, because that's the smallest distance. So then we calculate the distance to the end. We know that the shortest distance from North Bend to Yakima is 104, and the distance from Auburn to North Bend is 36, so that's 140, okay? So the distance from A to Y is 140. Since this distance is shorter than the previous calculated distance, we can replace it, okay? Because the previous calculated distance to A, let me scroll back up, was 175. See there? It's 175. So now, when we add Yakima to North Bend, it's 104. North Bend to Auburn is 36. That comes to 140. Now we can replace that distance because it's less. All right? We replace it. We mark North Bend as visited and designate A as current since it now has the shortest distance. Step 2, number 5. Are we almost done? I don't know. T is the only non-visited vertex leading to A. So we calculate the distance from T to Y through A is 20 plus 140 is 160 minutes. We mark A as visited and we designate E as current. Okay? So E is now current because A has been visited and now E is the only thing that we have left. It's the only non-visited vertex. And we calculate that distance, and that distance comes to 229 miles. We take the 172 plus 57 comes to 229. We're not going to replace that because 229 is longer than the 160. So we mark E as visited, and since all the vertices have been visited, we're done. So from that, we ascertain, from all of that, we come up with the shortest path from Tacoma to Yakima will take 160 minutes. You go from Tacoma to Auburn to North Bend to Yakima. Okay. Now, a lot of you are going to say, we could have just done this a lot easier. We could have just calculated the distances on each path and compared the totals. You could. That's called the brute force algorithm. Okay. Find every path leading from one vertex to the other vertex and calculate the distances and then find the least cost or the least distance. That's the brute force algorithm. The brute force algorithm will always give you the optimal and the best result. But it is not always the most efficient. It's usually not the most efficient. For a small graph like this, it is. It's fine. But what if you have a graph, what if you're working for a shipping company and you're trying to figure out the cheapest route to get your product from point A to point B, and you've got all these big US